So, any other questions? So, one more point which I must mention over here before we move forward is the following, that so this is actually one way to define P slash poly. Okay. So, you might see books or references where there is another notion of defining P slash poly, which is the following. So, okay. So, what we will look at is Turing machines that take advice. Okay. So, what is this? So, a Turing machine is said to take advice if in addition to its input x, it takes a string alpha mod x as input as well. Okay. And the point to be noted here is that note that alpha is the same for all inputs of a fixed length. Okay. So, alpha is a function, okay, which depends only on the length of the input, okay, it does not depend on the actual input. So, a Turing machine is said to take advice if in addition to its input, it has a string that is available to it. And now what we can say is we can give the following equivalence, that P slash poly is the class of functions for which there is a polytime Turing machine taking an advice of polynomial length. Okay. So, you can write the formal proof as an exercise, but the idea is very simple actually. So, given a problem in P slash poly. So, what is P slash poly? P slash poly is essentially a family of circuits, okay, which have polynomial size. Now, what I can do is that now each circuit I can encode it as an advice string. Okay. So, the circuit will have polynomial, each circuit has length that is polynomial in n. So, I can encode it as the advice string of that particular n. So, Cn is essentially the advice string for this Turing machine. And now this Turing machine with the circuit, as I said, we can just simulate the entire Turing machine, simulate the entire circuit, and that will be the output. That is one direction. The other direction is, suppose you are given a Turing machine which runs in polytime and also has a takes an advice string of polynomial length. How do you show it is in P slash poly? What is the idea?
Use this simulation and then hard code the advice.
Exactly. So, No, I mean how do you build the circuit? Huh. So, the circuit is basically just this simulation and you just hard code the advice into that circuit, okay, because it is just one advice string for the entire circuit, you can hard code it exactly. Okay, so this kind of shows that P is in well, yeah, P with polynomial advice is the same as P slash poly. So, now the next question is that we have P in P slash poly, how big is P slash poly? Of course, we know that these classes have these are non-uniform classes, they have undecidable problems. So, we cannot expect that they will be equal or anything even like that, they are not even, for example, there are even beyond exp in some, well not beyond, but there are problems in P slash poly which are not even solvable by any Turing machine, forget exp and exp whatever. But can I say at least the following? So, well, if P is not in P slash poly, the next question that arises is what is the relation between NP and P slash poly? For example, can we say that NP is in P slash poly, or can we say that NP is not in P slash poly? So, when I say NP is not in P slash poly, what I mean to say is that is there a function in NP which does not have polynomial size circuit. So, we know that every problem in P has polynomial size circuit, but can we say the same thing, I mean can we refute that for NP? And now because well, yeah, P is a subclass of P slash poly, if we are able to prove this, what would that imply? This would be another way of, this would be one way of showing that P not equal to NP, okay. And this is something that we again kind of, we hope it is, not we just hope, but we believe it is true, because well NP has very complicated problems, I mean problems where we have to kind of, we can only verify solutions, right. So, how can we design polynomial size circuits for it? It seems quite unlikely, and there are even results which show the following, okay. There are results which show that if NP is in P slash poly, then there is some de-randomization that happens, okay. So, that is quite unlikely. So, therefore, what researchers tried to do is that in trying, well, they tried to see that, well, can we relax this problem, okay. So, instead of showing NP is not in P slash poly, can we at least argue that NP is not in even some smaller size circuits or some smaller depth circuit. So, here the depth can be arbitrary, the depth can be as large as polynomial. Can we for example argue that it is not in constant depth circuits? So, for constant depth what is known is, if we move to constant depth over here. So, we have for example AC0, and there is this famous result by several people. So, first it was shown by FSS that the parity function, or I can also call it as the mod 2 function, is not in AC0, okay. So, this result was shown by first Sachs and Sipser in I think 81 first, then independently it was shown by Ajtai in 83. So, they showed that well parity does not, so if I look at a constant depth circuit for parity, then it would need super polynomial size, okay. Then Hastad basically improved this and showed I think in 84 or 85 probably, I do not remember. So, Hastad showed that not only will it require super polynomial size, it will require exponential size, okay. And his idea was to use this random restriction. So, we saw random restriction when we were proving Subotovskaya's theorem, okay. We will again revisit this result and we will show that any circuit which computes parity with constant depths will require exponential size. So, then the question was what if we go beyond parity, or for example, what if I kind of look at functions which are more difficult than parity, okay. For example, mod 3, mod 4, and what happens if I give those gates for free to my circuit, okay. So, what Rasborov showed is that if I look at, for example, mod 3 cannot be computed by AC0 circuits plus mod 2 gates. So, even if I give mod 2 gates for free to the AC0 circuit, it cannot compute, for example, mod 3. Okay. And Smolensky actually generalized this and showed that, well, if I want to compute some mod P, this is not possible with AC0 circuits plus some mod Q gate, where P and Q are co-prime. So, if I take, let us say, for example, 5 and 7 or even 5 and 6, if I give, let us say, mod 5 and, okay, let us take 5, let us take it for primes for the time being, 5 and 7, then mod 5 cannot be computed if I have mod 7 gates. Okay. So, the next thing is that, well, let me just say it for prime for the time, just co-prime where P and Q are primes. Now, the next question was, what if I give, let us say, both mod 2 and mod 3 gates, okay. That is basically I have mod 6 gates present in my circuit. What kind of functions can it not compute, okay. So, Barrington posed this open question that, well, if you look at the threshold function, okay, so this was an open question. So, threshold function is not in this class ACC, or just I can call it AC. So, what is ACC? So, ACC is basically the class of all functions for which you have and or not and any mod gates, okay. You can take any mod gates that you want, okay. And it is even kind of hard to compute threshold functions with this, okay. So, this proved very difficult to compute. So, the question was generalized further, that instead of, let us say, threshold function, what if I choose, let us say, a function in NP, okay. Take any function in NP, any problem, let us say the clique problem or Hamiltonian path problem, and can I show that, well, Hamiltonian path cannot be computed by an ACC circuit. So, again, just think of ACC, it is basically a constant depth circuit which has and or not and any mod gates. That is also, that was also not known, okay. So, for NP also it was not known. So, this is a question whether it is in ACC, okay. And not just NP. So, if you go, so let me write these classes over here. So, these are the complexity classes. So, you have, well, let us say threshold function, then I can go to NP, I can go to NEXP. Even we could not show that there is a NEXP function which is not in ACC. The best that was known is there was this class, well, the first thing that was known is if you have something in EXP to the power NP to the power NP. So, this powering means that you are taking an oracle gate which is a some NP function. Then there is a lower bound. In fact, there is a very large lower bound, that there are circuits of size, I mean, there is a function over here which cannot even be computed by circuits of size 2 to the power n by n. That is roughly what we get even by Shannon's theorem, okay. So, there are actually, So, NP to the power NP is basically I have an NP machine which is taking NP as an oracle, let us say which is taking SAT as an oracle. Yes, that class is more powerful than NP because for example, it can compute co-NP, it can compute problems in co-NP because I can directly give it a SAT instance and I can get whether it is unsatisfiable or not, but NP is not known to contain co-NP. Okay. Yeah. So, but anyway, we will not be even getting into these things for the time being. So, this is the thing. So, the point is that up to this level we had no idea, the only thing that we know was for very large class of functions. So, this was kind of like even embarrassing in some sense that we have such a large class, complexity class, but we can't even show that there is a function over here which is not in ACC, and this was shown by Ryan Williams in 2010 I believe. So, Ryan Williams showed that NEXP is not in ACC. Okay, so 2010 he exhibited a function, but again that is kind of the best that is known. So, I am just trying to give a roadmap of what we will be doing for the remainder of this course. Okay, so, as I said, we will be looking at Hastad's result of random restriction. We will also look at Rasborov-Smolensky's way of showing these results, these lower bounds, and this is basically by a very different method called approximating polynomials. So, we will design approximating polynomials for these various gates and then show this, and then we will towards the end of this course we will try to look at this result by Williams. Okay. So, that is all that I have for today. Okay, so, the last few weeks we have been in some sense looking at upper bounds. We tried to design circuits for various problems. We designed circuits for these arithmetic operations, efficient circuits. We showed relation between circuits and complexity classes, but now for the rest of the course, more or less for the remaining part of this course, we will be looking at lower bounds. We will try to see that why or how we can show that certain functions are not computable by certain circuits. So, ACC is basically constant depth circuits of unbounded fan-in that consist of AND or NOT and mod k gates for any k. Any k. Mod k gates is basically a mod k gate will evaluate to 1. So, it has input, let us say a mod k gate takes input bits x1 to xn. So, it would evaluate to 1 if sigma xi is let us say congruent to 1 mod k. You can define it anyway and it will output 0 otherwise. Yeah, you can have mod n gates also.
No, but I think the things it requires that there is a finite set of moduli for which gates are allowed for a given circuit family. Like for a particular function, all the circuits for that family should have moduli from a fixed, very constant size set of allowed moduli. Means this is actually equivalent to saying that there is just one modulus, but I don't think it can be allowed to be arbitrary.
I thought it can be allowed to be arbitrary. Yeah, so k, okay, maybe you are right. Yeah, I have to check. So, yeah, k does not depend on n. So, what you are saying is that this k is bounded. So, you can only allow mod gates up to some constant, and that can be replaced with a single mod gate of for some other k prime. Yeah.
But if we are doing that kind of stuff, then these kind of results are already showing that if we are allowing some mod k gates, then we can't compute certain other things.
If you are allowing mod k gates, then we can't compute what? How do you show? You are giving it more power, right? Yeah, so this is for very specific things. If 3 and 2 are primes, then this is happening. But what if I allow mod 6, then I can compute mod 3 very easily.
So isn't there any extension to this whether it's like co-primes or something?
So I have to just verify. So I thought it was true for co-primes, but it is for co-primes, yeah.
So then if it is co-prime, then suppose we allow mod k gates, then there will be some number which is co-prime to k.
Huh.
So then we can't compute the mod of that.
Yes, you can't compute by that same result. But it still doesn't say that, for example, if I take the threshold function, threshold is basically outputting 1 if the sum is greater than some k, whether you can compute this simple function.
So then, but that modulus will be in NP, right?
Which modulus?
That mod k, any mod k gates. Not this mod k, it's NP.
Yeah, they are in NP. Mod k are in P, in fact. But you are looking at the other now. You are trying to simulate ACC using an NP machine. But that anyway is not possible because you are looking at non-uniform things here and you are looking at uniform things here. So you can of course simulate any mod using just a linear using a log space Turing machine as well, right? But what about the non-uniformity? That non-uniformity cannot be done, right? We are looking at the other direction over here, that what questions in the uniform world cannot be solved by a non-uniform circuit which has very small depth.